All right, everybody, let's see. Just making sure that audio is working, and it looks like it is. Very good. So we are now starting a new unit. This is our Unit 10 surface area and volume, which ironically enough, we don't start surface area, I believe, until probably 10.3, 10.4, something like that. So we're not going to see any of that stuff until then. But what we can expect for right now is area, because we do need to have that skill first before we can do any of this other stuff. Okay. Well, we have our first key point here. Kind of revisiting this thing called a regular polygon. It's whenever we have those congruent angles and congruent sides for any polygon. So like for a quadrilateral, that would be a square. For the triangle, that would be equilateral triangle. And then from there, it kind of just, there's no like real specific name other than what the shapes are called. It's like pentagon, hexagon, and so on and so forth. But for our do first here, we have an example one. And what we're supposed to do here is we're supposed to determine, well, are these regular? So congruent, all sides are congruent, all angles are congruent. And they call it whatever it's supposed to be. So in this case, we have an eight-sided figure. So this is an octagon. And this one, it appears more so that the top and the bottom segments are longer than the other segments here. However, it's kind of a toss-up. I can go either way with that one. But it does appear that those top and the bottom are a little bit longer. So I would say not, but maybe regular. Who knows? Okay. And it is just kind of based off visualization. And it be possibly regular is not regular stuff. However, for number two, this one is definitely regular. It definitely looks like it has all the sides. And this is a pentagon because it has 5 sides. Next one, we have a hexagon. Okay, don't know why I did that, but that's okay. We'll keep going. Hexagon. And this is not regular, of course. Next one, we have a 7-sided figure, which is either going to be a sept or a hept. Okay, either one would work. This, again, is kind of just weird. Can't really tell. This is probably regular. Okay. Next one, we've already discussed what a pentagon is, so we already know what this is. But this is definitely not regular. Here we have a quadrilateral. We can't say and confirm if it's a rectangle because we don't know if the angles are 90 degrees, but we can say for sure it's not regular. And this is a quadrilateral. Okay. Next one, we have a decagon. D-E-C-A sided figure. And this one appears to be regular. Last but not least, we have another octagon. But of course, this one's not. That should have been pretty easy. When I did it in class, a lot of us seem to really understand this part, so that's very good. Next one, we have key point 2. Get all these notes down. The one I want to really kind of pay attention to is this word apothem, which is at the top right. Apothem is the distance between the center of a polygon to the side links, essentially. Okay, to the base, if you were. And it basically just kind of measures the height of the triangle it's created here. Okay. And so you'll see exactly what I'm talking about in a little bit about this whole like triangle business inside of this. But just for right now, kind of just keep it in the back of your mind. Okay. The other thing I want to keep some attention to is the central angle equals 360 over n. That is how we figure out, well, what the central angle is. And we must memorize that because otherwise we will not be able to get those points there. We must memorize this. Okay. Now, in this turn of talk, we talk about the difference between the radius of a circle and the apothem of a polygon. There is some similarities, right? They go from the center to some point on that shape, so the circle or the polygon. But what we'll see here is that the radius is typically, and by typically I mean really always, the radius is always going to be bigger than the apothem. Okay, and the example that I gave is if I have a circle, right, like this, I have a circle, and I were to draw, let's say, if I were to draw, let's say, a pentagon, right, to the best of my abilities, like so, and my center is this point right there, well, here's my apothem, but then my radius, oops, the wrong one, my radius this line right there. And you see that the radius is going to be a little bit bigger than the apothem. I would say that's probably the main difference. Okay. We have some examples. Let's kind of color coordinate what examples we're going to do. I'll do it one at a time. But we'll start with AFB. AFB is this segment right, or that angle right there. And we're told that this is a regular pentagon. Okay. And we're trying to figure out these angle measurements. Well, AFB is a central angle. We know the central angle because it's in the center, right? The angle is in the center. So we'll take measurement angle AFB equal to 360. Pentagon we said is 5 side lengths, or 5 sides rather, I should say. And you just kind of plug that into a calculator, or if you know how to do this in your head, perfectly fine. It's 72 degrees. Very nice. Then we're looking for measurement of BFG, and BFG is, I'm sorry, AFG. AFG, like so. Well, you know, this is another central angle, but it's half of the central angle that I was just working on. So let's just set it up like that. So the measurement of angle AFG is equal to half of the measurement of AFB. So, and so I can go ahead and put all that together. 1/2 times 72, the measurement of angle AFG is going to be equal to 36 degrees. Oh, I forgot to underline it. Well, last but not least, we have GAF, and GAF is going to be this angle in purple now. But realize that this angle in purple is part of a triangle. Well, I just found AFG to be 36 degrees. I know angle FGA to be 90 degrees, and I'm missing that third angle. Well, it's super easy for us. We could just take 180 minus 90 minus 36, and that'll give me my measurement angle GAF. So we do all that, we get the measurement of GAF to be 50 degrees. Okay. I would say relatively simple. Now, when you get to this slide, or we'll get to this part in your notes, I want you to cross off those bottom 2 equal signs. So like everything that's in this kind of part here, we're going to cross that out because I think it's a little bit more confusing whenever it's explained this way. And I'd rather just you keep this part right here. Okay, keep that part. Also, you do not have the core concept, but this in purple here, I want you to write where that is. Okay, so make sure you do write what's circled here on your paper, because that is how you identify what those 3 things are. In addition to that, this is on your reference sheet. It's going to be on the front where it says yes prep. And then if you look under area, it'll say regular polygon, and it'll show this equation. So it's that. The next thing is we're going to take this example 3 here, and we have to figure out what it's asking us to do. It tells us that there's a regular nonagon, which a nonagon is a 9-sided figure, right? Of course, you could have just counted it. But a 9-sided figure is inscribed in a circle with a radius of 4 units. And now we have to find the area of the nonagon. Okay, well, we just showed where, or we just told you where to find that reference, or where to find that equation. And of course, you can just look back at your notes. We know this is a 9 sides, like so. And so in order to solve this, I'm going to break it down in 3 steps. Okay, so kind of work with me here. 3 steps. I'm going to put step 1 over here. And step 1 is going to be central angle. Step 2 is going to be find A and S. Okay, and you'll see what I mean by that. And then the last step is going to be step 3, equation. So I'll break up the steps into some distinct coloring as well, just so you can see everything. Step 1, central angle. We've already found the equation to find a central angle. So we can say C angle equals 360 over however many sides we have. In this case, we have 9. And we divide that out, we get 40 degrees. So our central angle is 40 degrees. We look at our diagram, we would say that this angle right there is 40 degrees. But if I look at this triangle here, I know I have 4 for one side and 4 for another side. That means I have an isosceles triangle. But that's not really helpful to us right now. We don't really know how to solve things for an isosceles triangle. But what we do know how to solve things for is a right triangle. And so if we look at our apothem, again, it's the segment that is going to connect the central angle and the base of the triangle that we talked about earlier. See that the intersection between the two of them is going to be 90 degrees. So let's go ahead and just take a slice out of those two, out of that triangle. We'll take half of it to be more specific. And let's just redraw it. It'll be easier for us to see. So we'll redraw it. We have this triangle, 90 degrees here. 4 is across from the 90-degree angle. And our apothem is going to be the part that connects to my central. So looking at this problem here, I need to connect it to my left-hand side. Right, left-hand side. Right, yeah, that's funny. Because I know that this is going to be my central. Right, that little dot there is my central angle. And then for this third side, we're going to call it X for right now. Okay. Well, if I'm trying to find my A, I know my 4 is my hypotenuse. I need to think of the ways that I can possibly solve this. There are 3 possible ways, or really 4. We have Pythagorean theorem, in which case we can't do it all because we have no other information. Second one, we need special right triangles. Well, right now we don't even know what the angles are, so we'll put that in the back burner. The third one is similar right triangles, and that's just not going to work at all because we don't have multiple triangles. And then we have trigonometry, which again could work, but we don't know any angles, or do we? Remember, we cut this triangle in half, but we have that 40 degrees for our central angle. So it stands to reason that, well, that 40 degrees would have split in half as well. And so 40 degrees is now 20 degrees, but now where do we put it? We put it where the central angle is. We know that this has to be 20 degrees right there. Okay. So now we revisit. Do we have direct triangles? Nope. We need 45, 45, or 30, 60, 90. We don't have either of those. So we must use trigonometry to use here. Now, from my 20 degrees here, I know my A is going to be adjacent. Oops, I spelled that wrong. There we go. I know my 4 is the hypotenuse. And I know this X to be my opposite. Okay. Oh, now I gotta figure out which of my trig things to use. I have 20 degrees here to play with, but this 20 degrees in relation to my A is my adjacent. I have my hypotenuse 4. That's the only other number I have. So I need to figure out which one of the three things to use. So sine, cosine, or tangent. And if you're looking at your reference sheet, you would say definitely cosine. So we set it up, cosine 20 is going to be equal to adjacent A over hypotenuse 4. We're going to simplify because we want the A by itself. And we know for sure that A is going to be equal to 3.759 if we plug that into a calculator. Okay, so we found our A. Our second piece, find the S. Okay, well, the S is the side length of the nonagon. But our side length is being represented by this X here. But we'll see a little trickery here. Something that you have to really make sure that you're aware of whenever you see it. But we're going to solve for X now. Well, X is the opposite. We still have the hypotenuse. So let's go ahead and use sine. Find our X. But it's pretty much set up the exact same way, except this time we have sine instead of cosine. So you're going to do all the things. You're going to get X by itself, 4 times sine 20. We get X is equal to 1.368. So it's nice to have our X value, but remember, again, beforehand, we divided our triangle in half. So really, our S value is going to be 2 times our X. And so whenever we do that, we get S equals 2.736. Okay. And now our final step, our final step for the problem is just plugging all the pieces that I know into my equation. I found this equation on my reference sheet, A equals 1/2. I then found my apothem, which is 3.759. I found my side length value, 2.736. And I finally, or well, I didn't finally find it, but I did find my number of sides from the very beginning with my 9 here. And what happens is I get A equals 46.281. Remember, working with area, so we need a particular set of units. It didn't give us any units of measurement here, but we know it's going to be units squared. Do not forget the units squared. Okay. That is very, very important. Then we have extra example 3. Extra example 3 is very similar to example 3, as you can imagine. However, your step 2 is going to be slightly different. So my recommendation to you, follow the same pattern. So the step 1, step 2, step 3, but make sure that you're approaching the problem in the correct way. Okay, so take some time for that. And once you come back, you can look here. For this problem, just so I can actually, we'll do it the same way. We get our step 1. Oh, by the way, the answer is already there, in case you couldn't tell. Step 2. Have our step here. Okay. In step 1, we have to find our central angle. That's really easy. We have a hexagon here, so we have 6 sides. So central angle is going to equal 360 over 6. That'll equal 60 degrees. It's very easy. Then we have our finding of A and S. Well, looking at this triangle, it might be easier for us to kind of build off some things, right? So we know that we have a central angle C, a central angle of 60, I should say, so that's going to be 60. But then I also know that I have the diameter here. Well, this diameter is 32, which means my radius has to be 16. So these two are going to be 16. And, I know I'm supposed to have an isosceles triangle. Right? I know I'm supposed to have 16 and 16. Well, if I have 16 and 16, that means that the angles that are bases from them, or the opposite angles, are congruent. So I know that this is congruent to each other. The blue ones are congruent to each other right now. But if I subtract 60, which is my central angle, from 180, which is the measurement of all triangles, I get 120 left. But 120 divided by 2 is also 60. So every single one of these angles and the side lengths are going to be 60, because with hexagons, with a regular hexagon, it's going to be an equilateral triangle. Every other shape will not have an equilateral triangle, only for hexagons. So really, I've already found my S. My S equals 16. But I still need to find that A, and I need to draw that picture. Okay, so let's draw the picture. We know we have a right triangle. We know that the radius is 16. We've already found what the side length is, but because we cut our triangle in half, we'll start with 8. Well, if I know I cut that triangle in half, and I still preserve some of the angles I have here, this angle we've already established is 60, right? I'm just cutting it exactly from right here. So if you see where my cursor went, you'll see exactly what I'm talking about. If I have a 90-degree angle and I have a 60-degree angle, I know that the last angle must be the 30. And here I have a special right triangle, 30, 60, 90. The opposite side of 30 is A. The opposite side of 60 is going to be A squared root of 3. So this apothem must equal 8 the square root of 3. So we've found our A. And now that we've done everything we need to possibly do here, plug it into that equation. A equals 1/2 times the apothem, 8 square root of 3, times our lengths, times the amount of sides we have here, 6. And this answer is going to equal that answer right there. And I've already given the answer. Of course, if there are any questions, feel free to ask me any questions. All good. Move on. Now, this problem, we're not told some things. It's a little bit trickier for us. But we'll do what we can. So we're given that the radius is 19.6. Okay, well, radius doesn't belong in an octagon, it belongs in a circle. And so my recommendation for you, draw a circle as best as you can. That's not a terrible circle there. But if we have 15-inch sides, right, that's our S value, 15. We still need our A value, but we know that our N value, or number of sides, is going to be 8 because it says octagon. We just need to find that A value. Okay? Not difficult. We'll do the same approach. However, we'll abbreviate it a little bit because I need some more time to do other things. But I know I have a right angle right here. I know that these two angles have to be congruent to each other, which in this case, let's go ahead and figure out what that central angle is going to be. The central angle will be 360 divided by 8, which of course that's going to be 45, I believe. Oh, I see. Okay. Actually, we have an easier way to do it. We'll do it the way I wrote in my notes, because I think it's easier. If I have this value here to be 15, and I'm taking half of that triangle, it stands to reason that this value, that value, is 7.5, right? It's directly half of 15. And I know that the 19.6 is also applicable right here. So you know what we're going to do? Pythagorean theorem. 19.6 squared equals, right, because that's my hypotenuse, equals 7.5 squared times or plus b squared. We'll have that. I'm going to move the 7.5 squared and square both parts in one step. I'll get b squared equals, actually, I don't want to use b. Let's use a because it makes more sense with apothem, and a squared plus b squared equals c squared. So 384.16 minus 56.25. We're going to get A equals 18.108 as my apothem, and you're going to plug that straight into the equation. A equals 1/2 times the apothem, 18.8108, times the side length 15 times 8. So A equals 1086.48 inches squared. Okay, very nice. Okay. We'll keep going. We have, at least for me, a full page left, which is gonna probably take you a little over about 12 minutes. Try to do as fast as I can, given that I'm just simple. So, example 5. We must know that the area of a a kite and a rhombus is going to be 1/2 times the diameter 1 times diameter 2. And so if we know that information, we're going to go ahead and just do it, right? That's an easy equation, just multiplication of diagonals. Did I say diameters? I think it's diameters, not diameters. Diagonals. Diagonals 1 times diagonals 2 times 180. Okay, so make sure you know that difference. But if I have A here, my diagonal 1, 8. My diagonal 2, 6 times 1/2, you get 24 meters squared. And that's your answer. Really simple. This is on your reference sheet as well. For B, you get 10 times 7 times 1/2. You get 35 centimeters squared. Again, super easy, nothing to be really worried about. Okay. But now we have the last concept, 0.5. And this is the area of composite figures. Okay. I really don't think we're going to have a whole lot of this. But it is still a good thing to know and how to solve for it. Okay, you're going to take different shapes and you're going to basically just figure out the area of one shape, figure out the area of another shape, and however many shapes you have, then add them all up to get the total area. Okay, so I don't think we're going to see this a whole lot, but it's still, like I said, just good to know. Okay, so we'll look at example 6, and luckily for us, we have 3 examples. But I'm kind of just wondering if I should do all 3. Because I don't think we need to, given that we're not really going to see this. We'll do it this way. If you would like to see these problems, I already do example 3 in class. But A and B, if you do it on your own time, just ask me if I can check it for you. And we're just going to leave A and B alone because those 2 are the ones that take the most amount of time. Okay, we'll just do that. We'll do C though. Okay, I'll show you how to do C. C is actually really easy, right? We have a kite. And we have a parallelogram. And we know this is a parallelogram because the opposite sides are congruent to each other. We learned the theorem way back when. If we have opposite sides congruent to each other, we know that we're working with a parallelogram with a 4-sided figure. But the kite, like we just discussed, super easy. We know 7 times 6 is 1/2. Here we get 21 feet squared. However, the parallelogram is also just as easy. It's just going to be length times width or base times height, whatever way you want to say it. But length times width. In this case, we get 3 times 4. That gives us 12 feet squared. Then from here, because it tells us in key point 5 that we want a final answer, all the areas, you're going to add them up. So 21 and 21 and 12 feet squared, add them up, we get 33 feet squared. Okay, so that's how you do this lesson. If you have any questions, go ahead and ask me at an appropriate time in class, outside of class, all that stuff. But I hope you have a good weekend, and I will talk to you all later. Bye-bye.